This is APAB Calc. We are doing 2.3 and we're on to the quotient rule. So quotient is division, right? So we use the quotient rule when we have two functions that are in a quotient, right? One function divided by another, and it can't be simplified. Now, as we did with the product rule in our first set of examples here, E4 and P4, I'm giving you something that you would actually be able to simplify. I'm giving you something that I would not use the quotient rule for personally, just to show you that in fact the quotient rule does work the same as it would work if you're able to simplify. If I'm in the classroom doing this and I'm not talking to you on some random whiteboard sitting in my son's nursery, because that's the room we're in today, I normally do this like really cheesy dance that goes with the quotient rule that my high school teachers taught me in 1997, but I'm not going to do that right now, so maybe I'll save it for another day and I will do a video for you with the quotient rule dance. So here's the way the quotient rule works. I use H for the top function and L for the bottom because high and low. Literally, physically, the high function on top, the low function on the bottom. Some people don't use high and low. That's what I'm going to use. Some people use N for numerator and D for denominator, but I'm going to use H and L. So the quotient rule is low D high minus high D low, draw the line, square the low. That's how I memorized it as a kid in 1997. It's how I'm going to encourage you to memorize it too. I don't really care how you get it. You should make a note card for it, right? Your note card doesn't have to look like this. Your note card could actually physically have the phrase low D high minus high D low, draw the line, square the low. One thing I do want you to note is that quotients are not commutative. It matters which function is on top. Products actually are commutative, so like if I had an x squared times a sine of x, I could also rewrite that as a sine of x times an x squared, and that would be fine. But that's not true with quotients. So notice that there's a minus here. Subtraction is also not commutative. It matters which one of these is on top, right? And it matters that you remember there's a minus there. Okay, so we're going to walk through E4 and P4 the same way we did with E1 and P1, where we do it two different ways. So in E4, I gave you y equals 6x squared over x to the 6th. I would never use the quotient rule for this problem, ever, to be perfectly honest, but I'm going to walk you through how it would work with the quotient rule and show you that it's the same answer you get if you'd simplify. When we get to E5 and P5, then we're going to do some quotient rule problems where you would absolutely have to use the quotient rule. So if I walk through this with the quotient rule, so my y is 6x squared, that's my high function, over an x to the 6th, that's my low function. So my y prime is going to be low, so that's x to the 6th. D high is going to be a 12x, right? Minus high, which is 6x squared. D low is going to be a 6x to the 5th, right? Draw the line, and then square the low is going to be an x to the 12th, right? Because x to the 6th squared would be x to the 12th. So that's going to clean up on the top to a 12x to the 7th, right? Minus a 36x to the 7th, right? So I get 12x to the 7th minus 36x to the 7th over x to the 12th, which is going to be a negative 24, sorry, I'm out of room a little bit, x to the 7th over x to the 12th, which if I clean up is going to end up being a negative 24 on top of an x to the 5th, right? So my y prime was a negative 24 on top of an x to the 5th. Now let's do this the other way. Let's clean this up first. So option 2, let's clean this up. My y is actually a 6 over an x to the 4th, which is the same as a 6x to the negative 4th. Using the power rule, that means my y prime is a negative 24x to the negative 5th, which is definitely a negative 24 on top of an x to the 5th. Same answer. So again, I want to point out that no reasonable human would pick the quotient rule to do this problem. I mean, look how little work I had to do this the way we learned to do it in 2.2 versus how much work I had to do using the quotient rule. You don't use the quotient rule for a problem like this. You use a quotient rule for a quotient that cannot be simplified. And we're going to address that in the next set of examples. But let's walk through P4. So I'm going to erase my E4 to give me some room for P4 because there is frankly no room over here, right? So we're going to do the same two skills in P4, right? We're going to do it in both directions. So when I look at P4, so I'm going to bring my P4 over here, right? My y is a 5x over x to the 7th, right? If I do it using option 1, where I have a high function and a low function, I do the quotient rule. My y prime is low d high minus high d low, draw the line, square the low. So I get that my y prime is a 5x to the 7th minus a 35x to the 7th, all over an x to the 14th, which is a negative 30x to the 7th over an x to the 14th, I'm pretty sure my y prime ends up being a negative 30 over x to the 7th. Now, if I simplify this first and make my y into a 5 on top of an x to the 6th, which is the same as a 5, so that y is the same as a 5x to the negative 6th, right? So this is my other option, this is option 2. Then my y prime is going to be a negative 30x to the negative 7th, which is sure enough a negative 30 over an x to the 7th, same answer. Again, no reasonable human would be like, woohoo, quotient rule in this situation. Like, that's just not reasonable. All right, so now let's do some actual quotient rule problems, okay? In fact, I'm going to use the quotient rule to show you how you could find the derivative of tangent without knowing it. I gave you the derivative of tangent, right? But so let's do an example 5. Let's prove that the derivative with respect to x of tangent x is a secant squared. And we're going to do the same thing in P5, like E5, except we're going to show that the derivative with respect to x of cotangent of x is negative cosecant squared. All right, so let's just, again, I don't do this because I would ever make you figure it out from scratch, but just because, hey, it's a good way to show how the quotient rule works. So recall that tangent, right, so tangent is actually sine over cosine, right? That's what tangent is if you go back to your trig identities. So my high function is sine and my low function is cosine. So the derivative of this would be low d high minus high d low, draw the line, square the low, right? So that's going to be a cosine squared x plus a sine squared x, right? Because there's two negatives over a cosine squared. Well, if you remember your trig identities, sine squared plus cosine squared is a 1. So that's a 1 over cosine squared, which is the same as a secant squared of x. So sure enough, the derivative of tangent is a secant squared. Thank you, quotient rule. I'm going to give you a sec to try P5. Well, I mean, I'm not really, because you're going to pause me, so I'm just going to go ahead and do it. But pause me if you want to do P5. So remember that cotangent is cosine on top of sine, right? So that's my high function is cosine and my low function is sine. So low d high minus high d low, draw the line, square the low. Well, this is going to be a negative sine squared x minus a cosine squared x all over a sine squared. If you take a negative 1 out of that, you get sine squared plus cosine squared, which is a 1 based on that same trig identity. So you get that this is a negative 1 on top of a sine squared x, which is a negative cosecant squared of x. Check that out. So again, if you forgot your derivative rules, you could figure them out. All right, let's go ahead and do some other quotient rule problems. All right, so for E6 and P6, we're going to find y prime. All right, let's do y equals, let's do x squared divided by x plus, let's do 2x plus 3, sure. And for this one, let's do x cubed divided by 4x squared plus 1. Great, cool. Okay, so we're going to find y prime. So here my high function is the x squared and my low function is the 2x plus 3, right? So my y prime is going to be low, the whole low function, which is a binomial. D high is a 2x minus high, which is the x squared. D low is a 2, right? Because this would be a 2 plus 0, right? Draw the line, square the low. So I'm going to get that my y prime is a 4x squared plus 6x, right, when I distribute, minus 2x squared, sorry, my bad, missed the 2, all over this 2x plus 3 quantity squared. I would suggest that you leave this because it's already factored, and factored things are awesome, right? So factored means all multiplication, and there is no addition or subtraction, so this is a quantity 2x plus 3 times a quantity 2x plus 3. So the top is going to be, looks to me like it'll be a 2x squared plus a 6x all over a 2x plus 3 quantity squared. And that answer's great. If you want, you can take out a GCF of 2x on top and make this an x plus 3, but it doesn't really do much for you. Right? That's also a totally correct answer. I would only use this answer if I were asked to do something with my answer. But. All right, so pause me if you want to try P6. So this is my high function, it's my low function. So my y prime is low, d high, minus high. D low is going to be an 8x because the 1 will derive away to 0, right? Draw the line and then square the low. And again, I'm going to leave my low quantity squared as it is. So let's distribute and clean up the top. So my y prime is a 12x to the 4th plus 3x squared minus an 8x to the 4th, right? All over a 4x squared plus 1 quantity squared. My y prime is probably going to be written as a 4x to the 4th plus 3x squared all over this 4x squared plus 1 quantity squared. Or if you want, you can take out an x squared, but I don't really think that helps you much. 4x squared plus 3 over 4x squared plus 1 quantity squared. Either of those would be fine. I don't really think it helps you much to do the second one unless you were asked to do something with it. So that's pretty much the quotient rule. Let's see. Yeah, I think that's pretty much all right. Cool.